Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on the 4 cornerstones of a successful groundwater remediation project. With that, I'd like to introduce our presenters for today. We are pleased to have with us Jeff Carnahan, President of EnviroForensics and PolicyFind. Jeff Carnahan is a licensed professional geologist with over 20 years of environmental consulting and remediation experience. We're also pleased to have with us today Keith Gaskill, Chief Geologist at EnviroForensics. Keith Gaskill is a consulting scientist with over 17 years experience in the industry. We also have with us today Barry Poling, Central and East Region Manager at Regenesis. Barry Poling has over 17 years experience in the environmental industry. Also joining us today is Doug Davis, Senior Design Specialist at Regenesis. Doug Davis has over 24 years of environmental investigation and site remediation experience. All right, that concludes our introduction. So now I'll hand things over to Barry to get us started.
All right, thanks, Dane. So, when Jeff, Keith, Doug, and I sat down to put together the abstract for this talk, we asked ourselves what most people ask themselves: what do we want to talk about? Sure, we could do another presentation on a project that went well. We could show the technologies used and the great results. But the question was, how does that help the audience? What's in it for them? We really wanted to go beyond, discuss more than just the results. And that's what this talk does. This talk goes beyond the results and really tries to focus on how we got there, or how we get there as a group. And it was from this, the idea that the 4 cornerstones of groundwater remediation was born. These cornerstones are diversity, certainty, dynamics, and affordability. So to begin this talk, I'm going to do a brief overview of the common remedial technologies and give some guidance on the selection process. From there, I'm going to hand it over to Keith Gaskill. Keith brings a wealth of knowledge in the area of site investigation and remedial design. He's going to spend a little time outlining his 5 paths to achieve consistent results. As we transition into the 3rd cornerstone, dynamics, Doug Davis is going to provide some insight into his process as a remedial designer for Regenesis. Then both Keith and Doug are going to discuss their experience on a large chlorinated site in Indianapolis. And then finally, to round things out, Jeff Carnahan is going to discuss the idea of affordability and groundwater remediation. So with that, we'll get into the first cornerstone, diversity. So to present this idea of diversity, I'm going to show a graph that some of you may have seen before. Matt Burns presented something similar during his webinar last month. And if you sat in on any of our integrated site remediation talks before, you've likely seen this graph. It's simple enough, but it's pretty powerful. On the x-axis, you have concentrations ranging from low to high, and on the y, efficiency. So with high concentrations, think free product, what is the most effective means of remediation? This physical removal. Think pump and treat, dig and haul, SVE, those types of technologies. But there's a limitation to this approach, and the lower the concentrations get, the less efficient the approach becomes. The concentrations reach asymptotic levels, and no matter how much water you continue to pump, the concentrations just won't go down. I'm sure we've all seen that. This leads to the second step in the combined remedy approach, which is chemical. When we think of chemical, you can think of a class of technologies that includes chemical oxidation and chemical reduction, things like sodium persulfate or zero valent iron. Now, ISCO and ISCR, they have a bandwidth of success as well. Generally, from relatively high concentrations, less than NAPL type levels, to relatively low concentrations, low parts per million. In our experience, trying to reach MCLs with ISCO or ISCR alone is challenging and in many cases may not be practical. This is the point where we tend to transition into enhanced bioremediation. Generally, bio is effective from mid-range to low ppb concentrations and can be an excellent remedial approach to help you reach your final goal or your end goals. The real key with all of this is that these technologies are not mutually exclusive and combined technologies are needed for efficient treatment. I've listed here just the circles of technologies to give a little more insight into what is available and what we see. We all work in a lot of these different areas. And really just a diverse approach is what's needed in order to reach your goals. It's the main point I want to make there. And this final slide I'll leave you with is more of a graphical image of the same thing, showing the different technologies that could be used on one site. As we speak, EnviroForensics is working on a site in which they are using 5 of these technologies that are listed concurrently at the same time, on the same site, with sorption enhanced bio with liquid activated carbon, anaerobic bio, chemical reduction, bioaugmentation, and vapor mitigation. All of that's going on at the same time on the same property. And it's something that we commonly see as well. It's not unusual to see a combined remedy such as this for, specifically for chlorinated sites. So with that, I'm going to go ahead and turn it over to Keith and I'll let Keith talk to you a little bit about certainty.
Thank you, Barry. Good afternoon, everybody. I'm going to be talking to you for a little while about certainty as a cornerstone of successful groundwater remediation. As it turns out, clients and responsible parties want confidence that we know what we're doing. So we must do all we can to prepare and communicate and implement the best possible plan. In short, certainty is equal to results. These are the 5 cornerstones that I've chosen to highlight today. The conceptual site model typically comes before design. Collaborative design approach is the design process. Design verification of the initial test of the design. The design verification ongoing is the test and the dynamics during the design implementation. And the communication is throughout the process. So to concede to the first concept is a conceptual site model, and to succeed in remediation, you must have a high quality. You must have a high quality and comprehensive conceptual site model. Basically, that means that you have to have a release to receptor full story. The CSM is a continual process from the beginning of the project to the point of remediation design, and could be improved by the implementation and the data that we receive in that process. The CSM process helps, let me go back one. The CSM process helps diagnose data gaps and more effectively allows completeness than traditional iterative collection data and analysis. The CSM process aids in decision-making throughout the investigation and through remediation. Currently, EnviroForensics operates under the ITRC conceptual site model process. And we really like the process that we use here. I like to use an example of Occam's razor when developing a CSM. Many people think that Occam's razor means the simplest answer is the best. This is not what the philosophy suggests and is probably shortened and paraphrased. A side note is that the philosophy or concept works very well within the scientific method. In the CSM process and development, the idea is to eliminate variables that require assumptions through solutions, through testing. An example that I thought of was, let's say you're leaving work and you're going home and you want to mow the yard, and you don't know, you've heard that rain is in the forecast and you don't know if you have enough time. You would look at the radar and you would assume that, well, that's not going to get here very quickly, or that it's going the opposite direction. And then you would end up getting wet potentially. But then if you apply the motion feature on the weather radar, you've eliminated assumptions because you can tell which way the rain is coming, and you can tell how fast it's going to be there. So those require those assumptions. And in real life, that may be to test your well array to get your direction of groundwater flow and your plume direction, and then also to do slug testing or aquifer testing to determine the quickness in which it's going to get there. The more assumptions produce uncertainty. It's a better set of understanding, makes better remediation, so we need to produce less assumptions. Simpler hypotheses are more preferential to complex hypotheses due to testability. And try to keep it simple, and it becomes more cost effective. Now, how to improve your CSM quality? Systematic planning with involved parties from the start of the project on is a major portion of that. Data density and dynamic investigation is important. We've done a recent dynamic investigation where we did in 3 days what would have probably taken 3 years if we had done the old iterative process. And also we did 19 points and we're able to determine the flow patterns for the plume and fully delineate it. The early identification and elimination of data gaps. Doing slug testing early or grain size analysis early helps to identify, helps in our planning process for the long term. You minimize cost effectiveness and available resources. The MIP and other real-time tools, for example, are very good ways to maximize the cost effectiveness. And the second pathway is the collaborative design process. We work with multiple designers to identify and reduce potential chemical, physical, or logistical problems. And in the example here, the chemical portion of that would possibly be Doug, the physical would be me, and the logistical would be the project management team and Regenesis remediation services. And then the Regenesis team, which could potentially be Doug, Brad, RRS, and Barry, works with the environment forensics team, which could be the PM, the SPM, and the design lead to come up with a collaborative design. And then we develop the plan using the best practices, allowing some measure of flexibility in it. And Doug will discuss that measure of flexibility in the future here. A quote that I like here is, "Give me 6 hours to cut down a tree and I'll spend the first 4 sharpening the axe." That's from Abe Lincoln. What it says basically is that sharpening the axe represents the planning design process, and cutting down the tree represents the remediation. And that's not to say that you'd want to spend twice as much time on planning than you would the remediation, but that is to say that it's an important process and certainly would help the overall outcome. And the third pathway is the design verification, the initial design verification. This design verification is a process used to address target treatment zones as opposed to the CSM, which addresses the entire process. It's for specific unknowns. It's necessary for many in the in situ remediation projects to ensure success, but it does not replace the CSM, but enhances the understanding of the treatment zone. The initial phase of design verification is ideally conducted prior to the final design approvals on an application. This allows for a modification of design if needed prior to field implementation. Sometimes design verification is incorporated into a pilot testing program. Sometimes during the initial remedial MOB, we have to carve out a couple of days ahead of time to complete the initial design verification.
Thank you, Keith. This is Doug. We're going to talk a little bit about different design verification tests that you can do. And so we're going to go through some common examples here. First thing you see on your screen, soil core collection and detailed soil characterization or grain size analysis. We get a lot of logs and see a lot of logs that have been put together. And essentially, we're not trying to reinvent the wheel here. We're just trying to understand, what we're concerned about is what are the zones of transport for the contaminants and for the groundwater, obviously, and then where are contaminants being stored. So we're looking at it through a different lens there. The image you see on the bottom right is something we do in the field. This is a soil settling tube, and take a sample from your core, put it into the tube, add some water to it, shake it, and let it settle, and then you can get a pretty good qualitative, at least, and a semi-quantitative result from that, from doing these. So this is really helpful to ID those zones. Some other things you can do, vertical profiling. The image on the left, this is a site where the treatment interval is from about 12 to 70 feet. And you can see, if we were going to take an initial stab at this, that interval from about 40 to 50 feet, 35 to 50 feet seems to be where most of the contaminants are. So that's where we would want to come in and really put emphasis in our injection strategy. The image on the right shows vertical profiling in the sorb phase from the lab. And what you can see here is TCE results getting more concentrated or higher concentrations as you get into more fine-grained sediments. And we see that a lot with chlorinated solvent plumes. Another thing we do, this is an image from a site we've been working on here recently. This injection volumetric acceptance and reagent distribution testing. So this is pretty straightforward. You inject in a point and record breakthrough volumes and times at set points distance away. And you can see here we have 2 piezometers that we're going to be installed in the monitoring well down gradient, or I'm sorry, laterally from the injection point. Just a couple of other things here. MIHPT, so many of you on this call will be familiar with that. So this is a membrane interface probe. And what you're looking at there is a 5-foot, in between the red lines, a 5-foot zone, a sandy zone that where we're going to be injecting remedial fluids. But you can see, if you look at the XSD graph on there, the 4th column from the right, you see that we have a high mass zone below the zone that we're actually going to be treating. So this is a potential back diffusion situation in the future. On the right is passive flux meter data. And this is something we use when we really want to understand the mass flux coming in to our system, to our barriers in particular. And what this is a tube of carbon that you can put into a well, and as mass comes in, it gets sorbed onto the carbon, so you can do your time average mass calculations that way. And then there's also a tracer involved that gets displaced as the water comes through. And so you could look at groundwater flux coming through as well. And this gives you really, really good data, and probably is about as good a data as you can get right now when doing barrier type applications. So what's the value of design verification? The chart that we have here illustrates changes to the design following the initial changes to the original design following design verification. And what you see here, about 2/3 of the time we make changes. About 1/3 they're minor, about 1/3 they're significant, and 1/3 of the time there are no changes. So if you don't do it, probably there's going to be something that pops up and bites you.
Hey, Doug, real quick, regarding design verification, what is the cost impact of this? How does that affect your overall budget of the project?
Yeah, it's a great question, Barry. Cost impact is minimal. You know, in terms of the design verification itself doesn't cost that much. It's usually a couple % of the project. The impact to the overall scope, and most times we're able to work with the original budget that we set up, and actually we'll show a situation like that later. So that's most cases. So now I'm going to hand it back over to Keith, talk about design verification ongoing, and take it from there.
Thanks, Doug. The fourth pathway that I'm talking about is the ongoing design verification. This is once you're underway. This is when your remediation is taking place. You should conduct continual core testing during application to be sure that the conditions have not changed unexpectedly across the treatment zone. And you need to be sure that you're getting your expected ROI, and you need to do that as you're injecting. So if you need to make modifications, you can. You need to watch for other distribution issues such as subsurface short circuiting in utility corridors, such as if most of your points are going in at 4 gallons per minute and all of a sudden you have one going at 25 gallons a minute. There's something obviously going on there, and it could be short circuiting into a utility corridor. So you need to watch for those things. You need to resolve daylighting issues on site or get things onto the site that will help you with that. Remediation fluids on the ground are not as good as remediation fluids in the ground, and I think we all understand that concept. Some of these concerns may force you to make changes to the design on the fly. That's why we build flexibility into these designs, and we need to be prepared for changes. Sometimes we call this dynamic remediation. Doug will be discussing that shortly. And the last overarching one is communication. It is probably the most obvious, but among the most important. All parties need to be informed and have their appropriate say with the remedial project. Communication is an overarching part of the remediation project and must begin at the onset and continue throughout. Constant text, emails, and meetings may seem overwhelming, but if the design, implementation, and result is successful, it's all worth it. And that would be a good example of remediation certainty. So many of the pitfalls in remedial efforts can be avoided through proper communication. Everything goes right down to implementation, as we all know. And now I'm going to hand off the mic to Jeffrey Carnahan.
That's actually to me, Keith.
Oh, is it? My bad.
All right, so we're going to talk a little bit about dynamic remediation. Okay. Sorry about that. There's a little delay on the. There we go. All right, so here's our problem statement. In remediation work planning, sometimes preliminary is reality. So how many of you on this call have had this happen to you? Due to the pace of business, project stakeholders often want early definition of remedial scope, level of effort, and costs for an in situ injection remediation. And a lot of times they want that before we have everything completely figured out. So this forces an early commitment to scope and cost based on a preliminary remedial design. So preliminary designs, preliminary remediation work plans, they're formed using limited information in a lot of cases. At that stage, a lot of times we do have a good handle on the contaminant storage and transport zones, and the groundwater, some of the basic groundwater hydraulics, flow direction gradient, groundwater seepage velocity. But do we have enough for a successful design? You know, a common example here in the Midwest, we have glacial deposited soils, very high variability in soil grain size in 3 dimensions. So yeah, we may have an overall framework for what's going on, but relative to the target treatment area, we may need more. So here's a couple of design components that usually where we're lacking certain information to get a design that's going to achieve success. So the first one is the target vertical interval. And so you're seeing an image here from a cross section. You can see we got a couple points that extend into a lower unit. The middle unit there that's blank is a sand. There's some silt beneath that and some clay beneath that. And that bar in the middle is about a 10-foot vertical interval if you're looking at the average. But you can see that there's a range here of what we want to target, probably about 4 to about 15 feet. So preliminary design where we use that 10-foot average. When we get in the field, we're going to want to do some things to tighten that up spatially across our treatment zones. Second design component that where we typically need more information is injection point volumes and the spacing required. So those two go hand in hand. Off to your right is a figure showing kind of your what we call our theoretical radius of injection. And it is theoretical because as many of you know, you don't get perfect circles in your distribution or remediation fluid. But this is one way that you could look at it. And essentially here what you have is you take in the gallons per foot, your feet cubed per foot, dividing that by pi, and then dividing that by the porosity that's in play during injection. And that's different from the effective porosity in that it's usually a fraction of the effective porosity. So what will drain out of the soil would be termed effective porosity. What you're injecting is a different process because you're putting pressure behind it. And the pressure that you put behind it will also change that fraction up. So those are unknowns that we like to figure out ahead of time. So again, we mentioned design verification. Why don't we just do all this up front, get all this figured out? That's ideal, but that's not always realistic.
So Doug, quick question. How do you account for these data gaps if you can't get the information ahead of time?
Another great question, Barry. What we usually do in those cases is we put a little bit of set aside in the budget up front, and it's usually just a couple of percent. And so now we're going to talk about a site where we actually did that. And so this is a former industrial manufacturing site here in central Indiana. And what we have here at the top of the page, top of the figure here, you can see a red box. That's the site that we're working on. And within that red box, over to the right side of that red box is a building that's currently a storage, a warehouse facility. And you can see that there's a plume that goes about a quarter mile down gradient of that. And so our piece of the problem was up in that red box, and that's what we wanted to tackle. So this is our preliminary design. And you can see here we got 4 different components. You know, 2 of them are actually within enclosed building. And so we had spaced points out. They were about 20 feet on center laterally. We have another, a deeper zone, this south grade component 3. We're retreating a little bit of a deeper zone there, and then a barrier on the south side. And so we took this preliminary design. Oh, sorry, a little bit on the conceptual framework here. So those were the treatment areas. The first 2 top figures in this slide are showing the groundwater in 2 different layers, and then soil in 2 different layers. And you can see you got a groundwater, layer B, layer C soil, layer D groundwater, layer E soil. So this work was done by Keith ahead of time to determine where were our transport zones going to be, where were our storage zones going to be that are going to give us that back diffusion issue. And so put it together on a cross section like this, and those areas in blue, those are the areas that we were trying to target here for this remediation. So these are the sand zones, and you can see a little bit of clay popping through there on that top one. And this is, for this site, we use Plume Stop here. Plume Stop also with some bioremediation agents for remediation of chlorinated solvents, actually HRC and BDI. So why Plume Stop here? Plume Stop was used here because we wanted immediate reduction of groundwater in the groundwater transport pathway. We wanted to get that knocked out. But then we also wanted something that would give us a back diffusion prevention in the future. So we took that preliminary design, with those 4 areas, color coded them here. We had a range of target intervals of 10 to 25 feet, but we knew that within this range, about 50% on average was going to be permeable. And so splitting it, going in a little bit deeper, this is one of the areas, the east area. We broke it up into these smaller sub areas. And then what we did is we collected cores as we went. And as we collected those cores, we adjusted the treatment intervals to accommodate. And then we took the product budget that was allocated for that area of the site and then adjusted it up or down based on that information. So this is a real-time design change that we're making in the field. Also with dynamic remediation, for this to be successful, it takes a lot of planning. So it kind of seems like it could be seat of the pants, but it's not. It takes a lot of planning, and what you're looking at here is just a little snip of a schedule where we had outlined different areas that we were going to be working on at different dates. So everybody kind of know where we were supposed to be on track at a particular stage in the project. So you must plan well to pull off the dynamic remediation. In communication, I think it goes without saying, Keith said it earlier, must communicate well. It's just an example of some of the communication, kind of tying into that schedule. So the result of this is we had some obstacles, some things in the way. We had to block off certain areas, working certain days. It was overcome, 0 gallons spilled at this site. So that made the current property tenant very happy. Some other things that we did at this site, the ROI testing that we briefly touched on earlier. Now we set up something like this. Injection point, 2 piezometers, actually 3 piezometers, and then we had a well actually off the page. So we were looking at it for it in these 3 piezometers, 5, 7.5, 12 feet away. Also the monitor well at 15. We did the test. We confirmed it distribution out to the 12.5 mark, but not the 15 mark. So we knew we could get lateral distribution within the building at that 20-foot spacing successfully. And we also collected core samples just to show as a further line of evidence that the plume stop's getting there. And so the end result of this is before, you can see on the left, we have a core there from about 12 to 16 feet, which is right in the middle of the flow zone that we're targeting. You can see the before and after shots. Pretty obvious. You're getting more black, more of a charcoal gray color in the core to the right, indicative that plume stop is covering that interval very nicely. This is just a blow up through the center of that core. Also, confirming distribution in the monitoring wells. This just shows that we got distribution in the monitoring wells. This is one of the monitoring wells in the barrier. So results, this is really pretty straightforward. You can see the graph on the left is before, the graph or the Picture on the right is after 30 days, TCE, that central contour, I believe is a 500 ppb contour, so everything's been knocked out after 30 days. And then everything is knocked out again, at this point after 180 days. So we're maintaining complete reduction of the plume on site. Failure to plan is planning to fail. So all the things mentioned in the certainty and dynamics discussion cost money. Jeff Carnahan will now discuss the financial aspects of these remediation efforts.
Great, thanks, Doug. Appreciate it. I've been sitting listening to you guys, and great job, good projects, good cost-effective work. And I've heard everybody say the words cost-effective at some point during the presentation, and it just really brings home to me that as we contemplate the concept of affordability, it's important to understand that diversity, dynamics, certainty, the other cornerstones really are a big part of this fourth cornerstone, affordability. As scientists and environmental professionals, we love to spend most of our time addressing technical issues, but the reality is our clients and project stakeholders need our help as well with funding solutions. Typically people talk about affordability and it's like, just keep the costs down. But there's so much more to it than that if you really stop and think about it for a second. So I looked up the word affordability and several sources to see what we have. So the textbook definition is that to be affordable is defined as to be inexpensive, to have a cost that is not too high to bear. So think about that for a second. And also to be affordable, it is reasonably priced. So just to start with, let's step down through those for a second. No, sorry, inexpensive. Groundwater remediation is not inexpensive. So that one is a tough one, and we all just sort of have to bear that. Secondly, it depends whether something has a cost that is too high to bear. That's a relative concept. If there's no significant risk, then your evaluation of affordability is difficult. And also, it depends very, very strongly on the available funding. The more money you have, the more something appears affordable. That's a pretty simple concept, but it's one half of the balance of understanding what's affordable. Secondly, like I was saying, it depends what relief the responsible party and the stakeholders really need from the project, and that's the second piece of it. That's the counterbalance to the available funding. If there's no significant risk and a regulated closure is all that's really needed, then an expensive groundwater remedy isn't really affordable. That doesn't make sense. Conversely, if there's current risk, if there's exposure happening either from an on-site resident or an on-site occupant, or perhaps a third-party entity is providing some risk, that same groundwater remedy that was affordable, that not affordable a minute ago, suddenly becomes much more affordable. And of course, going further, even more affordable is a groundwater remedy when future risk has yet to even be quantified. That's something that we like to consider. What risks are out there around the corner? What risks can't we yet quantify? Can't we yet put a price on and truly evaluate affordability yet? In those types of situations, maybe the safest bet is to presume that a reasonable cost is affordable, and I'll talk about that here a little bit more. But affordability, again, is truly a balance between funding and risk. Let's say, for example, as a father, I'm trying to convince my son to take his car to get the oil changed. $1,500 a year for car maintenance is affordable if the risk of not doing it is going to result in destroying the car. It's something, it's a cost that makes sense and it's affordable. Bringing it a little closer to what we're talking about here, $500,000 groundwater remediation is affordable if the risk of not doing it's a $2 million lawsuit. So the other way that affordability was designed or is defined is that reasonable. Reasonable means that those costs are based on good sense. So in order for a groundwater remedy to be affordable, it has to be reasonable, and in order for it to be reasonable, those costs must be based on good sense. Reasonable costs impact the balance of affordability by effectively preserving the funding that you have into place. If the balance is how much money do you have versus how much risk do you have, if you can expend reasonable costs, you're preserving the amount of money that you have. A common phrase that we hear around here and around the industry quite a bit is what is reasonable and necessary. And that is paired very commonly with the concept of what is usual and customary. So those costs that are based on good sense are reasonable and necessary. And those costs that are based on good sense and as compared to those costs that would be incurred by others implementing the same action could be considered usual and customary. So there are a few things that we can keep our eyes toward whenever you're trying to keep overall remediation costs down and increase affordability. And they're listed here. The first thing you want to do always is develop smart remedial objectives. I think that Barry, Keith, and Doug have all incorporated a component of that into their discussion today. But the number one thing always, as you guys know as practitioners, is elimination of current and future exposure is number one. That's a no-brainer. And that has a key component to the balance of affordability. Eliminating current exposure is almost always affordable when you have a look at alternative risk. Beyond that, strike a balance between active remediation and long-term risk. I don't know if any of you guys have heard me speak before, but that's one of the things I like to have a look at. You know, invariably, when you look at the data and you look at the numbers and you look at the remedy and the risk, life cycle cost analysis show that the more money you spend on active mass reduction, you know, actually removing contaminant from the ground, equates to a lower overall project costs. And as I mentioned before, in those situations where you have risk down the road that has not even yet reared its head, has not even yet been quantified, the more remedy we can do now actually helps mitigate that risk and makes the project more affordable. Secondly, something to recommend is staying abreast of innovative technologies. I know most of us do that anyway because we are trying to maintain a competitive advantage. We're trying to stay ahead of our competitors. But you know what? A lot of times we're also looking for something that's cheaper. We're looking to improve on our current remedies to make things faster or make things better or just reduce the costs. And all of those things affect the affordability of our remedies. The third thing kind of goes without saying as well. So these are all very common sense, but stopping and looking at them is sometimes a good idea. Use qualified and experienced subcontractors that have proven track records, and actually you have seen them perform successful projects, if not for your own projects, perhaps for someone else's. You know, and again, not to sound like a commercial here, but there's a reason why we use Regenesis products so often and we use their remediation services so often. They've got a proven track record on our projects, and we enjoy those successes. Secondly, they've got a proven track record for budget adherence. You know, we can count on the team, along with Keith, along with this dynamic remediation process that has been talked about. It really has been a game changer when it comes to being able to keep costs down and keep them within limits to enhance affordability. So going back to the fundamentals of affordability, as we close up here, number one is how do we increase funds? You know, the easiest way to impact affordability is to have more money to spend on remediation. Many folks understand and utilize these resources, but many states have leaking underground storage tank trust funds for petroleum impacts. There are many dry cleaner trust funds across the country. I want to say there's 20 something states. I could be overestimating a little bit. Also, state and federal brownfields money or low interest loans. There are many sources of money available to help add to your funding source or your client's funding source. Albeit brownfields money are highly competitive and also typically we see are best used to augment funding as opposed to sole source of funding, but they're certainly available. Along those same lines, municipal TIF financing sometimes can be available depending on the developer and who the rest of the team is. But a lot of times we're seeing a lot of action these days in urban enterprise zones. It seems like any progressive city has some land set aside where they are willing to put a little money in your pot if you will redevelop or clean up within those enterprise zones. And then the fourth thing, which is insurance archaeology that I came up with as my list of 4 here. Anybody that knows enviroforensics knows that we do a lot of this type of work through our division Policy Find, but we are able to across the country for a lot of consultants, not just enviroforensics, but able to go back and help our clients identify and put historical general liability policies to use, and a lot of times fund the lion's share of the remedial liability. So I think with that, I want to throw it back to Barry for conclusions.
All right. Thanks, Jeff. Yeah, so that rounds out our talk on the 4 cornerstones. As you can see, diversity, certainty, dynamics, and affordability. Excuse me. I've got a couple key points here just to make before we migrate into questions. So first, you know, from just a remedial standpoint, there is no silver bullet in groundwater remediation. You know, we talked about diversity, and each project has different requirements and requires different technologies. So, you know, we'll be the first to tell you that you need to look at all of them, and that's where Doug, myself, the rest of our team from Regenesis, and I know Bioforensics as well, spends a lot of time trying to determine the appropriate technology for the part of the site. You know, secondly, design verification doesn't stop when remediation starts. And, you know, Doug's talk really highlighted that on this idea of dynamic remediation, and that continues throughout the process. You know, when you think about the way the environmental process goes in groundwater remediation specifically, it's very compartmentalized from a site phase 1 to phase 2 to site investigation to remediation, and many times those lines they appear to be black and white, but really they're gray, and that really carries over with the design verification and remediation. As part of that too, sometimes preliminary means reality. That's something that we're challenged with a lot. The number that gets presented early becomes the number that we all need to work from, or the budget we all need to work from. And, you know, Doug's talk and Doug and Keith's example with their site, I think hopefully gives some ideas or some tips and tricks on how you can how you can manage that process by building in some upfront money to account for design verification and that sort of thing. And then finally, affordability is a balance between funding and risk. And you know, Jeff did a really good job of summing that up for us. So I guess with that, I will open it up to questions. Anybody have anything else? All right. So bear with me here. Let me see. Feel free if anyone has any questions to post those. So there's a couple about the case study that was presented. Excuse me. So for the case study that was presented, the results showed a reduction of TCE. What about daughter products?
Yeah, so this is Doug. There were very little daughter products generated. We saw low ppb levels peak at about the 4 month or 3 to 4 month event, and then are already headed back down. So it did show up a little bit, but they're very, very suppressed, much less than you would see with a traditional enhanced reductive dechlorination where you're adding just electron donor and bioaugmentation agents. So I like to compare this to the daughters you would see with the plume stop, the liquid activated carbon as being maybe your Appalachian foothills versus what you might normally see, Himalayas. And that's the kind of comparison I like to see, and that's what we've seen at this site.
Okay, good, Doug. Along those same lines, were horizontal injection wells considered for injection beneath the building?
We did look at all sorts of different ways that we could get the substrate into the ground. But horizontal wells were an expense that we didn't need because we were able to apply the logistics that we did in moving around the interior components in an efficient way. So we did not think that the cost of horizontal wells was going to be cost effective.
Okay. Got a couple DVT questions here. So regarding design verification test, is the soil settling tube used for all investigation and all boring locations?
I think I'm struggling with the word all, so I'm going to have to answer no to that. Essentially what we're doing is we're trying to fill in those gaps in understanding. And sometimes we're correlating that back to investigative borings that are already been in place, but a lot of times we're covering the gaps in between. So I would say no to the all question.
Okay. And with the soil settling tubes, does that require any special kind of tooling?
Yes, 40 mil VOAs would be your special tooling. And so just simple glass vials, a little bit of water, and then whatever you need to get the soil out of the cores. So it's a pretty simple test. You know, you add the soil in, you add water, shake it, and then let it settle. And usually takes about 6 to 8 hours if you've got clay in there, clay particles, for those to all settle out. So it's something usually you collect it during the day, let it set overnight, and come back and take your measurements.
Okay, good. For the remedial agent distribution testing that you guys did, what types of wells do you typically use for that sort of effort?
So the examples we showed here, we use piezometers. A lot of times we like to tie in an existing monitoring well at the site too, just because it's another data point. But usually 1-inch piezos works out really well for that kind of test.
Okay, and I think this is a segue to the idea of distribution testing. How frequently do you change injection point spacing? from the original design?
I'd say it's pretty frequent. More commonly than not, we're going to modify point spacing, whether at the site as a whole or dealing with things that come up in the field that we talked about. We may get some areas where reagent distribution challenges or some surfacing where we know we've kind of flooded that zones, and a lot of times we'll take cores to document that. So the short, simple answer is very frequently, almost always.
Okay. Another question, what is the mechanism by which the plume stop stops or minimizes back diffusion? You want me?
So the mechanism that causes it to stop, so plume stop is activated carbon in a that's treated with a polymer surface coating. So the polymer will degrade after a short time, and then this allows the plume stop to then adhere to the soil particles.
All right. It looks like the rest of these questions are related to the presentation. Actually, I just got one more in. I'm going to ask one more. Okay. When gathering stratigraphic data for the site, from boreholes, when are you satisfied that you have enough information to proceed in remediation?
When gathering stratigraphic data. Sorry, so make sure I understand the question right. So when gathering stratigraphic data, when are we, I think it's going to depend on the site. Some sites are more complicated than others. What I can tell you is that most of these investigations, for most sites, we can get this work done in about 1 to 2 days in the field. And the more complex sites might extend more towards 3 to 4 days, typically not more than a week.
Okay, so it looks like most of the rest of these questions are related to the recorded webinar, copy of the presentation, that sort of thing. So I think with that, I will turn it back over to Dane to give a couple final housekeeping comments, and thank you all for attending the webinar.
All right, great. Thank you so much, Barry. So just before we sign off, just a couple of reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please do take a minute to let us know how we did. Also, you will receive a link to the recording as soon as it is available. If you'd like more information about environmental services from EnviroForensics, please visit enviroforensics.com. If you need immediate assistance with a remediation solution from Regenesis, please visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. Thanks again to our expert panel of presenters, Jeff Carnahan, Keith Gaskill, Barry Poling, and Doug Davis. And thanks to everyone who could join us. Have a great day.